All right, in this video, we're going to be working BC Homework 11.3b. We're going to be determining whether series are absolutely or conditionally convergent or possibly diverging. And with all of these, we kind of start off the same way. We consider first what would happen if we took the absolute value of the terms. So I'm going to say, all right, well, consider the sum n going from 0 to infinity of 1 over n plus 1 squared. Okay. Those terms are going to be 1 over 1 plus 1 over 2 squared, 1 squared, 2 squared, 1 over 3 squared. This is a p-series. So I would say converges by the p-series test. P equals 2, which is greater than 1. And that means that A converges absolutely. Because if we took the absolute value of the terms and added them all up, we would still be converging. So absolute. Okay. Then for B, we're going to see, okay, well, B is an alternating series, and it's kind of the same consideration. Okay, and this was actually going to work the exact same way. Cosine of pi n over n cubed root of n. Okay, so first we're going to take the absolute value of the terms and get 1 over n to the 4/3 converges by the p-series test. P equals 4/3 is greater than 1. I think I meant for something different to happen there. But that means that B converges absolutely also. It's good for us to see different forms of that. And then C, okay, I've got negative 1 to the n plus 1 times n squared over n to the 3 plus 2. Okay, in a multiple choice setting, we know this one's going to be conditionally convergent because it's bigger on bottom by exactly 1, like the harmonic series, but it's alternating, so it's going to do the same thing as the alternating harmonic series, which is, say, conditionally converge. Okay, but first we have to take the absolute value of the terms and say, okay, what's going to happen with this? N squared over n to the 3 plus 2. This one's going to diverge by limit comparison. Limit comparison to the harmonic. Okay, so in order to establish that, we would need n equals 1 to infinity of 1 over n diverges. No reason needed for that. Everyone knows the harmonic, it diverges. And then limit as n approaches infinity of n to the 2 over n to the 3 plus 2 divided by 1 over n. Okay, that limit's going to be 1 is positive and finite. Okay, now that I've determined that it is not absolutely convergent, now I'm going to check for, is it conditionally convergent? And yes, the terms of C alternate and decrease in magnitude to 0. That's going to give me the fact that C converges, and because C converges, but the sum of the absolute value of the terms of C does not converge, that means conditionally convergent. Now, for number 2, more of the same. We're going to look at this one. N cosine of pi n over n plus 2. Wait a minute, this is degree 1 in the numerator and the denominator. Okay, so this one is going to diverge because the denominator is not even growing faster than the numerator. The cosine of pi n, remember, that just causes it to bounce negative, positive, negative, positive. But otherwise, it's just n over n plus 2. That is not the type of thing that we'd even consider converging, so I'm going to do the nth term test on it. The limit as n approaches infinity of n cosine pi n over n plus 2. Doesn't exist, but, you know, really it's like, because the limit's not equal to 0, that gives us the divergence of A. B, negative 1 to the n over 2 to the n plus 1. So we're thinking about 1 over 2 to the n plus 1. Okay, and this is one where, okay, it looks geometric, but it's not exactly geometric. And we could do limit comparison against a geometric series. Like, you totally could, and if that's what you feel more comfortable with, you can do that. But I'm going to say that this one converges. I'm going to do direct comparison because I can tell that the denominator is just 1 bigger than the series with 1 over 2 to the n, which we already know converges because by a geometric series test. So I'm going to say 1 over 2 to the n plus 1 is less than 1 over 2 to the n. I just thought that one was, like, I could see it, so I'm going to take that opportunity rather than doing all the limit work. And over 2 to the n converges by the geometric series test. R equals 1/2 is between -1 and +1. All right, then over here, C. Oh, look at that. The series is not actually alternating, right? Because I believe, yeah, -1 to the n cosine of pi n, plug in n equals 2, you get -1 times +1. No, +1 times +1. So it's going to be positive. Plug in n equals 3. You get -1 times -1. Okay, so the series is actually the same as the sum from n equals 2 to infinity of 1 over square root of n. Okay. I'm not just considering the absolute value of the terms here. I'm saying that this is actually what C is equal to, and I'm going to say, well, I know what happens with that. It diverges by the p-series test. P equals 1/2, which is less than or equal to 1. All right, next we are going to find the values of k that make the series converge conditionally. Okay, so converges conditionally is where we are alternating and bigger on bottom by an amount, by a positive amount. We do need to be bigger on bottom because we need to be converging by the alternating series test. Okay, so I know that k needs to be greater than 2, right? Because if k was equal to 2, the terms wouldn't even be going to 0. If k is less than 2, again, terms are not even going to 0. Okay, but we also know that when we're bigger on bottom by more than 1, like if k was bigger than 3, we would go absolutely convergent. Okay, so I think I'm gonna, if k is greater than 2, no, I'm kind of backwards. I was saying that was part of my answer. If k is less than or equal to 2, diverges. And that's not converges conditionally. If k is greater than 3, it converges absolutely. So that means that if we are greater than 2, but less than or equal to 3, we'd have conditional convergence. All right. Now we're going to find the values of k that make the series converge absolutely. And that's where we need to be bigger on bottom by more than 1. So here I've got into the 1/2 into the k. This is, if I rewrote it by kind of simplifying with the powers, I'd be saying, whoops, -1 to the n plus 1 times n plus 1 over n to the k plus 1/2. Okay, so I need, let's say, point out that here I have degree 1, here I have degree k plus a half. And I need k plus a half to be bigger than 1 by an amount more than 1. Okay, so k plus 0.5, power of the top, I mean the bottom minus the power of the top has to be greater than 1. So that's k minus 0.5 greater than 1. Yeah, k greater than 1.5. That's what I was thinking, but yeah, it seems obvious now, but I was just kind of having doubts about it. And we were having doubts, so let's just solve for it algebraically. All right, so this series converges absolutely. Oh, yeah, I know this. I really like this problem. If you remember what I said, about how to test for absolute convergence, then it kind of leads you in the right direction on this. Determine if S, which is a sub n multiplied by sine of n, is absolutely convergent, conditionally convergent, or divergent. Justify your answer. It's like, how am I going to do this? First time I saw this question, that's what I was wondering. Like, how am I going to show this? I wasn't even sure what I was leaning towards. But once I started, putting pencil to paper and saying, all right, if they're telling me that this series converges absolutely, let's say that gives me this fact. I kind of didn't realize, the first time I worked this problem, I didn't realize that that's what I kind of needed to start with. But if I want to determine if S is absolutely convergent, conditionally convergent, or divergent, I'm going to take the absolute value of its terms. So we're going to consider the sum in going from 1 to infinity of the absolute value of an sine of n. Okay. Looking at that, I'm looking at absolute value of an, that series converges. I need to do a direct comparison, the absolute value of trig. That's kind of a giveaway for direct comparison. So I'm going to do that direct comparison and say, okay, I've got absolute value of an, and I've got absolute value of an multiplied by sine of n. And I know sine of n is a number between -1 and 1. So the thing on the right, the terms on the right have to be smaller than the terms on the left. So, okay, like that. But I know that the sum of, like, the red fact is true. The sum of the absolute value of an converges. And these terms are even smaller. So that means that this thing here, n equals 1 to infinity, of the absolute value of an sine of n converges. And that means that S converges absolutely. So this is a problem that's just like perfectly set up for a direct comparison. Okay, now next, why is the alternating series test not applicable to this series here? Well, I'm kind of, I see 2 -1 to the ends. It could be that it's not alternating. It could be that the terms are not decreasing in magnitude because I'm adding a -1 to the n. I do think that the limit of the terms is going to be 0, though, because the 2 -1 to the n's, they're never going to get bigger than 1 or -1. Yet that square root of n is going to grow, so the limit of the terms is definitely 0, but I can't tell, is it the alternating or is it the size of the terms? So I'm going to just start with n equals 2. -1 to the 2 is positive 1 over root 2 plus 1 minus 1 over root 3 minus 1 plus 1 over root 4 plus 1 minus 1 over root 5 minus 1. Okay, that's got to be enough terms for us to see the pattern. Oh, pardon me, I recording on a different device than usual, and I don't know how to pause this recording, so I'm just, kind of taking it in one shot, and then didn't predict sneezing during the video, but I'm usually able to avoid that, but pardon me. Okay, so I think that, root 3 minus 1 is a number between 0 and 1, because I know that root 3 is between 1 and 2. Okay, so 1 over a number that's between 0 and 1, then plus a third minus 1/5 minus 1 is just, or it's root 5 minus 1 is just a little bit bigger than 1. So 1/3, 1 over a number that's a little bit bigger than 1. These terms are not decreasing in magnitude because they are alternating. Okay, I could have probably realized that by process of elimination, but kind of needed to convince myself. Don't decrease in magnitude. All right, now on to a power series type question. So suppose f of x is equal to n plus 1 x to the n over n squared 6 to the n. This one is very similar to the series question from the 2024 BC exam. And so determine whether f of 6 converges absolutely, converges conditionally, or diverges. Justify our answer. We can do that. So f of 6 is going to equal the sum n going from 1 to infinity of n plus 1, 6 to the n over n squared times 6 to the n. Okay, well, the 6 to the n over 6 to the n, that's always going to be 1, so I'm actually going to get rid of that. Remove it from our consideration. Okay, we know what's going to happen with this series. It's going to diverge by limit comparison to the harmonic. But actually, wait a second. N plus 1 over n squared, that's going to be bigger than 1 over n. Yeah, because, n equals 1, 1 over n would be 1. But I've got 2 over 1. N equals 2, I should have 1/2, but this is 3/4. Oh, yeah, direct comparison is going to be the way to go. So I'm going to say n plus 1 over n squared is greater than 1 over n, and the sum as n goes from 1 to infinity of 1 over n diverges because it's the harmonic series. Okay, so f of 6 also diverges. Good opportunities for direct comparison here. Determine whether f of negative 6 converges absolutely, converges conditionally, or diverges. Justify our answer. So f of negative 6 is going to be just like f of 6. Oh, I erased it. So f of negative 6 is the sum n going from 1 to infinity of, it's just going to end up being, actually, n plus 1 negative 6 to the n divided by n squared 6 to the n. Now I'm going to take these terms off to the side and kind of investigate them. Or actually, maybe I'll just take the 6 to the n's. So I'm going to say negative 6 to the n over positive 6 to the n. Okay, the exponent does distribute over multiplication and division, but it does not distribute over addition and subtraction. So I could say that's like negative 1 to the n times 6 to the n divided by 6 to the n and cancel off that way. Or because both of these things are taken to the nth power, I could say that this is equal to negative 6 over 6 to the n. Either way, we need to be able to cancel this off and realize that this is negative 1 to the n, which is going to cause the thing to alternate in sign. Okay, and now that it's an alternating series and it's bigger on bottom, I know that it's converging. Okay, the terms are decreasing in magnitude and they have limit 0. But if I'm trying to determine if it converges conditionally or absolutely, I'm going to take the absolute value of the terms. Okay, if I do that, I'm going to see that n equals 1 to infinity of absolute value of negative 1 to the n times n plus 1 over n squared diverges. I just showed that in number 7. Okay, but f of negative 6 has terms that alternate and decrease in magnitude to 0. Okay, so that means that f of negative 6 converges, and since we already showed that the sum of the absolute value of its terms diverged, that means f of negative 6 converges conditionally. Right. It can be shown that f of negative 3 equals, okay, we plug in negative 3 and we get negative 1/2 to the n, along with the other stuff that we're familiar with, and that the first 3 terms of this series sum to S3 equals negative 125 over 144. Okay, that's nice, but I don't think we actually need to know the value of that. Show that the absolute value of the difference between f of negative 3 and s sub 3, the absolute value of the difference between the true value and the approximated value, that's error. So I want to show that error is less than 1 over 50. And with these, and I have not considered f of negative 3 yet. This is another series that's alternating because of the negative 1/2 to the n, and it's certainly growing faster in the denominator than it is in the numerator, so it's going to converge. So I'm going to start there before I use the alternating series error bound. So f of negative 3 is alternating. The magnitude of the terms is decreasing. And limit is 0. Just figured I'd written the sentence a bunch. I haven't done the 3 bullet points in this video. For the alternating series test, it doesn't matter to me. You can do it either way, and it doesn't matter on the free response section of the AP exam. We just need to kind of hit all 3 of those ideas. Alternating, decreasing in size, heading towards 0. So n plus 1 over n squared times negative 1/2 to the n. That limit is 0. Okay, so f of negative 3 converges. Okay, now that I've established that, I'm going to do that alternating series error bound. So in this case, error is less than or equal to the absolute value of the next term. And if I use the first 3 terms, that's n equals 1, n equals 2, n equals 3, I just need to plug in n equals 4. So that's n plus, not n plus 1, 4 plus 1. Over n squared would be 16 times negative 1/2 to the 4th. Less than equal to 1/50th. Oh, yeah, I see it. It's okay. So, whoops, pardon me. I don't necessarily recommend doing this. Just get your error bound and say it's less than 1 over 50. If you have the time and you need to convince yourself of why it's less than 1 over 50, we can go off to the side and do a little bit of scratch arithmetic. It's always there in like some sort of way that you can see. So 5 over 16 times 2 to the 4 is another 16. Okay, you could either think of this as 2 to the 4, 2 to the 4, and count by powers of 2, 2, 4, 8, 16, 32, 64, 128, 256, or maybe you just know that 16 times 16 is 256. That's not one that I had to learn in elementary school. So either way, this is 256, and that is definitely less than 5 over 250, which is 1 over 50. So that's how it works. All right. But if just because I realized that, I don't get any more credit than I would have had I only just verified the convergence and then done the error bound that way. All right. Write the first three non-zero terms and the general term of f prime of x. So do I already have f written out in its terms anywhere? No. All right. So f prime of x. All right. So all we're going to do is take the derivative with the power rule, but I'm going to remind you why that's true. So n plus 1 is 2 over 1 squared 6 to the first, x to the first, plus n equals 2 is going to be 3 over 4 times 36 x squared. This is where I branched off from the 2024 problem. N equals 3, that's really all I need. Is going to be that n equals 3 term, which is going to be 4 over 9 times 6 to the third. Ooh, okay, well, I should be able to simplify that if I need to. Plus dot dot dot. It's 3 non-zero terms and the general term. All right. Now, if I want to take the derivative of that, I'm going to try to keep it in the frame. If I take the derivative of 2x over 6, I'm going to get 2 over 6, okay, plus 6x over 4 times 36, and 4 times 3, I might leave it like that for a second because I'm thinking I'm going to simplify this. 9 times 6 to the third. Yeah, there should be ways I can simplify that. Okay, and then plus dot dot dot. Then the general term, what did we do? We brought the power down, n times n plus 1. We subtracted 1 from the power, and we really didn't do anything with the denominator. N squared 6 to the n. Yes, great. That's the general term. I should probably have a plus dot dot dot. I'm pretty zoomed out here. All right, now if I'm going to go simplify this, that's going to be 1/3. 6 and 36 is 1/6, so 1 over 24x plus. All right, well, let's see. I'm going to take that 6 to the third, and I'm going to make it 3 to the third and 2 to the third. Yeah, I like that. So I'm going to end up with 2 powers of 3 and a 2 down here. All right, 9 times 9 is 81, times 2 is 162. Yeah, plus. I don't think there's anything I can do with this. Divided by n squared 6 to the n, and so on. All right. Now, if I plug in 0 to f prime of x, because this is what f prime equals, if I plug in 0 there, I'm going to get 1/3 plus a whole bunch of zeros. Yeah, that's just going to equal 1 over 3. Right, now I've got another power series problem, and this is mostly, I kind of wanted to have a 4th page problems for this homework, but also because, one of the students in my class expressed to me that, you're doing all right with series generally, except for the power series. And, at this point in the course, you don't really need to be worried that much about power series. Not a huge deal. But they are going to be a huge deal in the next unit. So I just figured I might give us a little bit more familiarity in a low-stakes environment like the last page of the homework. So I'm going to say approximate the value of g of 1/2 using the first 3 terms of the series. That's pretty familiar. That's going to be doing stuff, we did in the last lesson. So g of 1/2 is approximately equal to 1/2 minus 1/2 cubed over 3 plus 1/2 to the 5 over 5. Okay, there's not really any point in simplifying that because it's going to be a really unpleasant, uncommon denominator situation. I think I'm going to have, what, 8 times 3 is 24 in the denominator, and 32 times 5 is 160. 24... I don't think that it doesn't divide 160. So, maybe looking for some least common multiple. I don't think so. No need for that. We can just stop at 3 terms. What's the maximum possible error in our approximation? Okay, now I wanted to say error. I stopped at that term here, so it's going to be the absolute value of the next term. Absolute value of negative of 1/2 to the 7 over 7. Okay, and that is true, but in order to justify my answer, I have to first verify the convergence of g of 1/2. So I'm going to say that terms of g of 1/2 are alternating and decreasing in magnitude to 0. Okay, and that allows me to use the alternating series error bound like that. Now we're going to write the first 4 non-zero terms and the general term for g prime of x, okay, just like we did before. I might just say, all right, the derivative is going to be 1 minus 3 over 3. Okay, nice. That cancels. Oh, and then that's going to happen every time. And look at that, plus dot, dot, dot. The series is still alternating, so I shouldn't be surprised that I've got a -1 to the n. But when I bring down that 2n plus 1 for the power rule, it cancels off with the 2n plus 1 in the denominator, just like I saw in all the terms. So I subtract 1 from the power, and I've just got x to the 2n. So I'm going to say 1 minus x squared plus x to the 4 minus x to the 6 plus -1 to the n, x to the 2n, and beyond. All right, that's great. G prime of 1/6, and I think this one was from 2023. This is something that we can do. 1 minus 1/6 squared plus 1/6 to the 4th minus 1 over 6 to the 6, and so on. This is a geometric series. Okay. I don't know. I think it's easier to see in the formula here that the ratio, the conjugate ratio is -x squared. Okay, and the negative of the square of 1/6, that's definitely going to be between -1 and 1. Okay, this thing converges. I need to verify that convergence before I use the sum total formula, though. So I'm going to say this series converges geometric ratio equals the negative of 1/6 squared. Okay, that is -1 over 36, but okay, I realize I'm at the bottom of my document. So I'm going to say the sum is going to be first term, which was 1, multiplied by 1 over 1 minus -1/6 squared. Okay, so 1 plus a 36th is going to be 37 over 36. And so 1 over that is going to be 36 over 37. All right, there you go. And that was pretty solid homework. And that's going to be all for this video. Thanks for watching.